Welcome, this is Dr. G, and in this video, we're going to continue on in the moles unit and talk about molar mass. I'll first define what it is, we'll learn how to calculate the molar mass for atoms and molecules, and then finally, we'll use it as a ratio in our mole conversion questions. You got this. Come on, let's have some fun. Let's go! In order to do the molar mass, you need a periodic table. Unfortunately, periodic tables can be very different. Not in terms of the elements, that should be the same, but in their molar masses. Some periodic tables go all the way up to like 4 or 5 or even 6 decimal places, while other periodic tables are more beginner friendly and they will usually round to the nearest whole number or the nearest tenth. In my video for the mole unit, I will be using the rounded numbers and the simpler numbers because I don't want to spend half the videos writing decimal numbers. So at the end of the day, just double check with your teacher and use the periodic table that your teacher wants to use or provides you guys with. Let's start by looking at fluorine. That number 9 on the top, that's the atomic number or the number of protons. The number on the bottom, that you've learned before as the atomic mass. But from now on, it can also be known as the molar mass. So what does it represent? It represents 1 mole of fluorine is equivalent to 18.99 grams of fluorine. Or, in other words, it is the mass of 1 mole of your element, and that mass is always measured in grams. All right, these 3 words all describe the same thing at the end of the day. They're going to be the exact same number, and they all represent the mass of an atom or a molecule per 1 mole of that atom or molecule. However, depending on which chemistry course you're taking specifically, whether you're in AB or regular or AP or honors, you're going to come across 1 or more of these words. So what is molar mass? Molar mass technically implies that you've experimentally measured the mass, but at the end of the day, it doesn't matter. People will use that word even when you're just reading it off the periodic table. The units for molar mass is grams per mole. In IB, they don't like to do the fraction for some reason, so they do grams with a mole -1, a negative exponent rule. The middle one here, the molecular mass, that's probably the least important of the 3. This one is just implying that you've theoretically calculated it, and the units is Daltons, but whatever. The last one is relative molecular mass, and this one's pretty big in IB. Again, it's the same thing as molar mass, except now the mass that we have is used as a ratio to 1/12 of carbon-12. Whatever that means, it doesn't matter. The number is the same. The key thing is there's no units for relative molecular mass. Let's take a look at how we can use the molar mass as a ratio to help us in mole conversions. Let's use fluorine for an example here. We've established that 1 mole of fluorine is equivalent to roughly 19 grams of fluorine. Well, if they're equivalent, then we can set them up as a ratio or a fraction, can't we? We can either do 1 mole of fluorine over 19 grams of fluorine, or we can do the other way around, 19 grams of fluorine over 1 mole of fluorine. Again, remember from my previous video, you don't have to choose which ratio to use when you're doing a question. The correct ratio will show itself as long as you focus on getting rid of the units of the things you don't want. When it comes to the molar mass of molecules, you will actually do some calculations on your own. 1 mole of water is equivalent to 18 grams of water. More on how I got that in a second. But for now, since this is equivalent, we can set them up as a ratio of 1 mole of water over 18 grams, or the other way around, same thing as before. Let's take a closer look now at how I got 18 grams per 1 mole of water here. Water is H2O. In this, we have 2 hydrogens. Let's take a look. Each hydrogen has a molar mass of 1. So if you have 2 hydrogens, that's 2 times 1, which is 2 grams. Okay, what about oxygen? Well, oxygen has a molar mass of 16, and there's only 1 oxygen, so that contributes to 16 grams here. And if you're to add these 2 numbers together, we get 18 grams per mole of water. So as a rule, if you're calculating the molar mass of a molecule, you just have to add up all the atoms that makes up the molecule, and that will be the molar mass of that molecule. The molar mass of water can be written 2 ways if you're using it for mole conversions. You can either put the moles on the top with the grams on the bottom, or you can do it the other way, right? But if they're asking for the molar mass, if they really do want just the molar mass, or they're giving you the molar mass as a piece of information, which one of these two is the actual definition of molar mass? Is it 1 mole per 18 grams of water, or is it 18 grams per mole? Remember, the actual definition of molar mass is the grams per 1 mole. So if the question's asking you to find out the molar mass of something, you must leave your answers in grams per mole, or if you're an IB, of course, you can just do grams and then mole -1. Let's practice some calculations for molar mass, starting with sulfuric acid, or H2SO4. Well, to find the molar mass of this compound, we just break it down to its individual elemental components here. We have hydrogens, we have 2 hydrogens, each one is 1 grams, so that's going to be 2 grams. For sulfur, each one is 32.06 grams, we only have 1, so that's going to be 36.02 grams. And then finally, we have 4 oxygens, 16 grams each, times 4 will be 64, and then we add up all of these masses to give us a total molar mass of H2SO4 of 98.06 grams per mole. Okay, you can give this one a try here. Pause the screen, and then you can check if your answer is right. All right, did you get this? And the last compound here, don't worry about the dot with the 2 H2Os. That's just a hydrate. It doesn't really mean too much when it comes to calculations. You just have to just include the water in your total mass. So, give it a try. Did you get this? All right, let's move on. Now we got 4 examples before we wrap up this video here. For each of these examples, feel free to pause the screen and then give it a try on your own and then come back and see if you did it right or not. All right, so let's take a look at this first question. 2.25 moles of AgCl was extracted in a reaction. What is the mass of AgCl that was extracted? What do they want and what do we know? Well, they're asking for the mass of AgCl, so that's what they want. And they gave us 2.25 moles of AgCl, so that's what we know. Starting off with what we know, we're going to multiply it by a ratio right away. Do they want moles? No, they don't. So we have to get rid of it. And we have to do that by putting it on the bottom here. And we're going to put what we want on the top, which is the mass, in the unit of grams of AgCl on the top. And then we ask ourselves, can we do a ratio between the moles and grams? Yes, we can. That's molar mass. And it's always an unknown amount of grams, which is from the periodic table, per 1 mole of AgCl. So now let's figure out the grams. Let's look at the periodic table right now. Can we find Ag? There it is. And what about chlorine? There it is. Add that together and we get 143.4 grams of AgCl. Now we can cross out the moles and we're left with grams. Double check, is that what the question wants? Yes, it is. So then we calculate this and we get 332.65 grams of AgCl. But notice in the question, we only have 3 sig figs, so we got to round this to 333 grams of AgCl as our final answer. Next question. This one's a bit longer and you'll see why. The question says, how many atoms of chlorine are there in 2 kilograms of magnesium chloride? Well, again, what do they want? They want the atoms of chlorine, and what are we given? We're given 2 kilograms of MgCl2. So starting with what we know, we see that we have a problem because we're starting off with kilograms. Now, we know for sure we don't want kilograms because they want atoms, but a bigger problem is we can't even use kilograms in molar mass. We can only use grams. So right off the bat, we're going to multiply this by a ratio, and to get rid of kilograms, we have to put it on the bottom, and we're going to put it as a ratio with grams. It's just a unit conversion here. 1,000 grams is 1 kilogram, and then we can cross out the kilograms. Now we're talking. Now we're in grams, but we're still nowhere near to finish because they want atoms. So we got to get rid of our grams, put it on the bottom here. What ratio can we use with grams? Moles, that's it. So we put moles on the top, and now it's going to be 1 mole for, let's take a look at the periodic table here. Where is magnesium? There it is. And chlorine, there it is. Keep in mind here, it's MgCl2, so we need 2 chlorines. We add that up, and we get 95.2 grams of MgCl2. Cross out the grams. Now we're at moles. Are we there yet? No, we're not. Keep going. Goodbye to the moles. What can we put with moles here? Now, they want atoms. We can't just go from moles straight to atoms if they're asking about an atom within a molecule. In this case, the molecule is MgCl2. So we can only go from moles to molecules first, and that is going to be 1 mole for every 6.022 times 10 to the power of 23 molecules, Avogadro's number. Now we can cross out the moles. We're at molecules. We're almost there. Now we can finally get rid of the molecules and put a ratio with atoms. We look at MgCl2 and we ask, How many atoms of chlorine are there in one molecule of MgCl2? Well, there's 2 atoms for every 1 molecule of MgCl2. So there it is. We can cross out the molecules. And finally, we are at atoms of chlorine. Now we crunch this into our calculator and we get 2.53 times 10 to the power of 25 atoms of chlorine. Double check the sig figs. We only have 2 sig figs in the question. So that means we have to round it down to 2.5 times 10 to the power of 25 atoms of chlorine. All right, example 3. What is the molar mass of a protein if an individual molecule of that protein has a mass of 1 times 10 to the power of negative 17 grams? Well, what are they asking for? They want the molar mass of a protein. I know, that's a bit weird. We'll talk about that in a second. And what did they give us? Well, they gave us that an individual molecule of that protein has a mass of 1 times 10 to the power of negative 17. Okay, let's address the fact that they actually want us to figure out the molar mass. What units do we need to have in our answer? Recall, molar mass is grams per mole. That means in our final answer, we better have grams on the top and moles on the bottom. Keep that in mind. Okay, now when it comes to what we know that 1 molecule of that protein has a mass of 1 times 10 to the power negative 17. So we can write that down, but we can't write it on its own because that mass of protein only applies when you have 1 molecule of it. So it's kind of like a ratio in its own right. So we have to put it over 1 molecule of that protein. What do I want to get rid of here? Do I want to get rid of my grams on the top, or do I want to keep it there? Do I want to get rid of my molecules on the bottom, or do I want to keep it there as well? Our goal is to get grams over moles. So I'm completely fine with having grams on the top. What we need to get rid of is the molecules on the bottom. If you want to get rid of something that's currently on the bottom, where do you have to put it in order to cross it out? Yeah, you gotta put it on the top now. So this time, we're gonna put molecules of protein on the top so that we can cross it out with the bottom one later on. And what ratio do I wanna put with molecules? Well, they want moles on the bottom. And of course, we can put molecules with moles. So let's do that. We're gonna put moles on the bottom. And the ratio is Avogadro's number, 1 mole for every 6.022 times 10 to the power of 23 molecules. And at this point, we can cross out the molecules, leaving us with the original grams on the top that I didn't want to get rid of, and the moles on the bottom that I introduced. That's grams over moles, and that's good because that's molar mass. Crunching in the numbers here, we get 6.022 times 10 to the power of 6 grams. Checking the sig figs, we only have 2 sig figs in the question, so we got to round this to 6.0 times 10 to the power of 6 grams per mole of protein as the molar mass. So this question is a great reminder that if you want to cancel out a unit, you don't always put it on the bottom. If the unit starts off on the top, like we usually do, then yeah, you have to put it on the bottom in the next ratio to cross it out. But in this case, the molecules, which is what we don't want, started off on the bottom. So to get rid of something that's on the bottom, you have to multiply it by a ratio and put that unit on the top. Okay, example 4 is different from the first 3 examples in that it's not a mole conversion question, but it's focusing strictly on the molar mass. Let's take a look. What is element X if the hydrate X2CO3 with 10 H2Os has a relative molecular mass of 285.99? Notice that there is no units for this because it's a relative molecular mass. It's the same thing as molar mass, remember, with just no units. Okay, the second thing is the hydrate. The hydrate looks a lot more complicated than it actually is. Just treat it as one huge compound with 10 H2Os in there. Now, they're asking us for the element X. We don't know what it is, and the only way to figure it out is to figure out what is the molar mass of this element, and then we can figure out the name because that is its identity. So let's list all the different elements in this compound. First, we have X. No idea what the molar mass is, but we know there's 2 X's in this compound. Next is carbon. We know carbon is 12 grams as per the periodic table. We only have 1 carbon, so carbon only contributes to 12 grams out of the total molecular mass. Next is oxygen. There's a total of 13 oxygens. Multiply that by 16 grams per mole, which is 208 grams per mole for oxygen. And then finally, we have hydrogen. There are 20 hydrogens. Each one, as per the periodic table, is 1 gram per mole. So hydrogen contributes to 20 grams per mole. Then we can add all of these grams up to get a total of 240 grams per mole. That's contributed by my carbon, oxygen, and hydrogen. So if I take that out of the total of 285.99, that 45.99 must be due to my X2. So let's think about it. If X2 gives me 49.99, then what is the mass or the molar mass of each individual X element? We just divide 45.99 by 2, and that is going to give us 22.99 grams per mole. Now we know that element X has a molar mass of 22.99 grams per mole. All we have to do now is look at the periodic table. Can we find an element with 22.99 or 23? There it is. That's sodium. So our final answer, the element X, is sodium, or Na. Let's continue on with the mole conversion map that we started in the previous video. Now we know that we can go from moles to mass. And the way to do that is through molar mass. How do we do molar mass? Well, it can either be 1 mole over an X amount of grams, or an X amount of grams over 1 mole. Notice the asterisk. To find out the actual number of grams, you have to refer to the periodic table. All right, and that's molar mass. I hope it helped. I hope it clarified how we can use molar mass in mole conversion questions. It's quite important because it'll show up a lot in the future questions you do in chemistry. If you like the video, give the video a like. And if you really like the video, feel free to subscribe to the channel. I would really appreciate it. It will help the channel grow. If you have any questions, comments, or topic requests, remember you can always put it down in the comment section down below.